Now we're going to look at the travelling wave solution. All right, so let's have a look at Berger's equation. So it was dtu plus u dxu is equal to nu dx squared u. So we're going to guess that the solution of the form travelling wave solution, we always do the same thing, right? We say u is equal to u of, okay, you can introduce some new function, but x minus ct. And we substitute that into that equation and we end up with an ODE. So we get minus c u dashed plus u times u dashed minus u times u double dashed equals 0. Okay, now we can actually solve this exactly, and we'll talk about how to do that in a second, but we're going to just, first of all, we're going to look at the thing from the phase plane and have a look at what the solutions look like. So we introduce the variable w, which is du d zeta. Remember, zeta is this travelling wave coordinate. That's w, and so the equations become du d zeta is w, and w d zeta is the second derivative of u with respect here, the second derivative here. So I rearrange this equation, I get 1 over nu w times u minus c. Okay, so that's all standard stuff. What's a bit weird here is that the equilibrium points, we're going to have w as 0 from here, and then of course that immediately satisfies that. So we don't have an equilibrium point, we have an equilibrium line. So the entire u-axis is an equilibrium point. So this is a kind of a degenerate system. We maybe haven't seen these before. So let's have a look at what happens there. So maybe it's easiest just to talk to the notes here. Here's the picture of this phase plane for the system here, written up here. Du dz is w, etc. Just for some typical values here. And what happens is the equilibrium, the whole line's equilibrium. You get one solution that leaves here at minus infinity and goes at and arrives here at plus infinity. And there's a whole family of these solutions. You get an infinite number of solutions of this travelling wave, okay, coming from different equilibriums. Okay? And of course this depends, these have different speeds and different heights. Okay? We'll see that shortly when we solve the equation. And there's the picture of those solutions drawn as the travelling wave. And there's a solution.
So we're going to start on Berger's
equation.
So this is the final,
starting from some initial block.
And it basically, it's a different equation, but it's the same idea as we've seen
that, but you can't sort of get the solution going from one
not
going
identical,
down here.
But there's nothing really
other problem
radically new here.
All right.
The exercises you did
So we're going to
get rid of the
this
shock
whole family of
by
travelling
adding
waves.
this
So we're
term
going to actually
here,
solve this system
which is
exactly.
some kind of diffusion. So basically, as it
So
starts to
equation
get
was
towards a shock, this term
minus.
keep
It's
mu
quite
small.
useful to see the solution written down in that equilibrium and look
So
at
as
it
we
from
start
that
to approach the
perspective.
shock,
It probably isn't
this term here, which is
totally
normally small,
standard
suddenly
way to
starts
look
to
at
become
the-
large because we get a very
textbooks
large
probably
change
wouldn't
in
go that
the
way with
row. Okay, so the curvature goes up.
the equation,
And
but
it
I quite like
corrects
to have a
it
little
and
picture of
smooths
it,
You actually saw
so
you
we
got the same
understand what's going
solutions.
on. So here we go. Here's the
All right.
solution.
So what we do, Berger's equation,
So we
is
can
just
integrate this. We get minus
simplest
cu
version of this. It's dtu
plus
as
this
c
is the
becomes u
this is the derivative of a
plus
half u
u
squared
times dxu
minus u times u
is
dash
equal to mu dx.
is equal to some constant c1. It's a little
Okay,
bit
but
tricky
it's
here what's
actually,
going on. C
Berger's studying,
itself is a constant, and so
turbulence
is
or something like that
c1.
in fluids. He
So
came
we
up
can
with this
rearrange
equation.
that equation.
You know, this
u
equation
dash
to try and model that.
is equal
So
to...
and we still don't understand a lot about turbulence, and we're not fully sure about where to go with Berger's equation.
U squared minus
all these
2cu
nonlinear equations. But let's
minus 2c1.
have a look at this.
So this is more or less...
equation. So what are we going to do? We're going to do three things. We're going to find the travelling wave solution.
Right? This is where it gets a bit tricky, maybe, or a bit odd, because this is just basically any quadratic.
We're going to...
We know the only thing we know is the
solve numerically, and we're going to use our split step spectrum.
More or less. Like how long as it starts
We've already done. You actually have already solved the equation numerically. So
how do we solve this equation?
Easy to solve.
So what we do
in 3 is we're going to find an analytic solution.
We basically say that this is equal to u minus u1.
Now it's interesting in these times. One of the features of these problems is the analytic solution is probably more complicated to program and just to use than the numerical solution.
There might be complex roots, but we're not going to get anywhere with that. We won't get a solution to this equation. We won't have a travelling wave solution. So we've got 2 real roots, and we actually know that these are the equilibrium points where u doesn't change. So when I maybe just go back to that picture in the phase plane where I had the solutions coming out of here from here to here. This was u2 and this was u1. You can sort of see that if you do a phase line here. You have an equation here for u dashed is equal to, we're assuming here that, without loss of generality, that, a bit weird, u2 is the small one, u1 is the big one. So u lies between u2 and u1. Alright, so when we look at the phase line, here's the 2 equilibrium points. And then the flow is down here like that. Leads one, comes down to the other. This flows up. Okay. But we're only interested. There's a solution that leaves here at minus infinity and flows down to here. That's the travelling wave solution. So let's solve this equation here. Just get rid of this phase line. This picture. Okay. And then try and solve it. So we've got 2 u dashed is u minus u1 times u minus u2. So then we rearrange that and we get it's separable, right? We get du over u minus u1 times u minus u2 is equal to the integral of d zeta times over 2 nu. Okay. And I'm going to pull the solution out of the hat. I'm pretty sure one of the assignment questions should be is to solve this equation, to go through all the nightmare of working it out, separate, you got to use partial fractions. It doesn't seem too much of a nightmare actually. So we get a half u1 plus u2 minus a half u1 minus u2. I believe there's room here that I'm not going to run to my picture. All right, there's the solution. You can add a constant onto that, obviously. There's but we want the solution to go from plus and minus infinity to a starting point. Okay, when it's at minus infinity, tau hyperbolic tangent of infinity is 1 and minus infinity is minus 1. Okay, so it starts out, we apply some boundary conditions that u of minus infinity is minus infinity, u of minus infinity is u1 and u of infinity is u2. Those are the boundary conditions. All right, so there's a solution. We've got an exact solution for that travelling wave, and I can probably risk just here take a gradical colour, this crazy green. The solution looks like that. There's u2 and there's u1. Okay, it goes like that between the two. Not very exciting.